This is a rather densely packed video about statistical inference. I'm going to cover a wide variety of techniques. I will show you enough to know how to do them, although each of these techniques could be covered in an entire lecture or video in its own right. And there are places you can go to get videos to go into detail on these. So I want to try to sort of stay at a high level, more like the 50,000 foot level, so that you can sort of see that all of these techniques bear a certain similarity. I mean, they're all asking the same basic question. The way they go about answering it differs from technique to technique. I'll show you a little bit about how each of those techniques work, but the more important point is to understand the big picture. And since the computer does all of the sort of tedious, dirty work for you, you get results pretty quickly. The real emphasis is on trying to understand what those results are telling you. So the data set I'm going to use for this is a very simple data set. It consists of 117 houses that were for sale in Albuquerque, New Mexico. And I think it's circa early or mid 1990s. So these prices, you can't buy houses in Albuquerque for these prices anymore. These are relatively low by today's values. It's not truly a random sample of houses. It was actually, I believe, taken from the newspaper over a 3-month period. So it's not a random sample, but there were houses for sale. I actually don't think there's any particular bias in this sample as far as the sampling goes. More important question here has to do with the measurement, which we know is sort of systematically off. These are listed prices in newspaper ads, and most houses don't sell for what the listed prices are. They sell for something less than that. And it's not a universal kind of constant percent discount that they sell for. It may depend on the price of the house as well as other characteristics. So there are measurement questions given that these are not sales prices, these are listed prices. I'm going to ignore all that though and just consider this a random sample of 117 houses for sale in Albuquerque in that time period. So the first thing the thing we're most interested in probably is the price of the house. Let's just look at that alone. Let's analyze the distribution of the price of the house. And what you see is it's a somewhat skewed distribution. If you were to overlay a normal distribution on this, it doesn't look like it's normally distributed. Fit a normal distribution, not terrible, but it's clearly, the green is skewed. It's not symmetric like a normal distribution would be. Let's just remove that so it's not cluttering up the picture. So the mean is 106,000 plus, a little bit more than that. Notice the standard deviation, 38,000. There's a lot of variability among individual house prices. Notice it also gives you the standard error of the mean. What is that? That's the standard deviation divided by the square root of the sample size. So that gives you 3517. And that's a measure of how much variability there would be from one sample to the next, one random sample to another of a size 117. Notice how much less it is than the individual variation. It's on the order of 1/10 as large. So individual houses vary a lot, but the mean of a random sample of 117 houses is a much narrower range. And that's where the confidence intervals derive from. It's approximately plus or minus 2 of these standard errors on either side of that mean of 106,000. So the confidence interval goes from 99,000 to 113,000. So suppose you were interested for some reason in whether or not it was safe to say that the selling price of homes in Albuquerque in this time period, the average price is greater than 100,000, or let's just say not equal to 100,000. Could it be equal to 100,000? Well, look at the 95% confidence interval. It goes from just under 100,000 to well over 100,000. On that basis, you'd have to say, if you want to be 95% sure, you would not be able to rule out 100,000 as a value. We could approach this with a hypothesis test. Not there. You go here, you can go to test mean, specify the hypothesized mean. Suppose we think it's 100,000. If you knew the standard deviation, you would put it in here, and we would be using a standard normal distribution to conduct this test. Since we don't know the true standard deviation of the population, otherwise we wouldn't even be doing a hypothesis test, we would just know what the true mean is. You're never going to know what to put in here. If you don't put anything in here, we use a t-test instead. But if you look at a table, the t-table and the standard normal table when the sample size is 117 are virtually identical, so it doesn't really matter. So just put in your hypothesized mean of 100,000, and here's the result. What the result shows is it takes the, it's giving a test statistic. This test statistic is constructed by basically saying how far away from the hypothesized mean is the mean that we found, which is $6,273.50 above the hypothesized mean. But how far is that above the hypothesized mean measured in standard errors, standard deviations associated with the sampling distribution? Well, since the standard error of the mean is 3517, this difference of 6273.5 turns out to be 1.7837 standard deviations above the mean. That's what that red line in this picture is indicating. We're hypothesizing that the true mean is at 100,000. What have we found? We found the red line, which is at this distance, and this p-value, 0.0771, is the sum of these two blue areas. It's measuring if the true mean were 100,000, how likely is it we would get a random sample of 117 houses to be this far away from 100,000, away on either side? 7.71%. If you believe in this magic 5% number, which I don't, you would have to say, well, if I need to if it needed to be less than a 5% chance that we could be this far away just by random chance, I'd have to say we haven't met that standard of proof. Beyond a reasonable doubt, we can't say that 100,000 is not the mean. We are unable to reject that hypothesis. We don't want to say 100,000 is the mean because we can't reject 100,000 as the mean. All we're saying is we have insufficient evidence, just like I went over in the previous lecture. Notice there are two other p-values given. These are called one-sided p-values. If you were testing the hypothesis that the true mean is less than 100,000, then the only area we're interested in is this brighter blue area, which is half of this 7.71%, 3.85%. Miraculously now, we would be able to say we can reject the hypothesis that the true mean is 100,000 or less, because we're sufficiently far above 100,000 to reject that hypothesis. The one-sided hypothesis test, one of them is always going to be exactly half of the two-sided hypothesis test, because this t-distribution, which is this bell-shaped curve, is symmetric, and the area that far away on one side has to be half of the area being that far away on the two sides. The other p-value, 96%, is these two one-sided p-values always weigh up to 1. So basically, if this is 3.8%, this one's got to be 96.2%. And this hypothesis with a very high p-value, this one-sided hypothesis, would be a meaningless one to ask, because it's actually testing the hypothesis that the mean is 100,000 or greater. Remember, hypothesis test is geared to setting up a hypothesis that you want to then see if you have enough evidence to disprove. Well, just think about what we're doing. If we're testing a hypothesis that the mean is over 100,000 and your evidence is that the mean is 106,000 in the sample, could that evidence ever be used to disprove that the mean is 100,000 or greater? Clearly it couldn't, because the evidence is consistent with the hypothesis you're testing. So in terms of disproving the hypothesis, you'd never be able to do that with evidence that's consistent with the hypothesis. So you shouldn't even be asking, you should not interpret the 96% the 0.96 p-value here, it's a question that on the surface you should immediately say, there's no way I can disprove that hypothesis. If I'm really trying to test, could it be 100,000 or greater, and I have a sample that's greater than 100,000, you haven't proven anything, and you can't disprove that hypothesis. So you basically shouldn't be bothering to look at the p-value. You'd have to say, we can't possibly disprove that hypothesis with this evidence. We could potentially want to say we have sufficient evidence to disprove the hypothesis that's 100,000 or less, because that one-sided p-value actually is less than 5%. We're almost always interested in a one-sided hypothesis test because we always care about direction. We're interested in whether something is bigger or less. Are we ever going to really want to know, is the mean value of houses equal to 100,000? We want to know if it's greater or if it's less, not if it's equal to. So the two-sided hypothesis test is almost never intuitively what we're interested in asking. But by convention, that's usually the p-value we look at. When you see a paper that is published that says we did a one-sided hypothesis test, it should raise a red flag in your mind, because the usual reason why people would report a one-sided p-value is because they can get one that's half as big as the two-sided p-value. And if you want to be able to say we found something significant, a lower p-value means we can say that in cases where the two-sided p-value might not say you have enough evidence, like in this case. So by convention, the 0.05 number is usually what people look at least for published work, and it's usually a two-sided p-value. In any case, that whole idea of dichotomous thinking of it's either not equal to 100,000 or it is equal to 100,000 is really the wrong way to think about it. What we have is we have a sample with some evidence, and based on that evidence, go back to the confidence interval, I sort of believe that the real mean value of homes is somewhere between 99,300 and 113,200, at least with 95% confidence. If I want to be more confident, then the range would have to be wider. If I'm willing to be less confident, it'll be narrower. And you can ask JUMP to give you a different confidence level, so you can get the confidence interval 90%, 99%, whatever percent you want. 95% is the standard or what's reported. I'll also show you there is a little animation that JUMP provides here. If you do the p-value animation, here's just a picture of what the hypothesis test is doing. If the real mean, which you're hypothesizing is 100,000, if it was 100,000, the red would describe what you would expect to get by taking a random sample of 117 houses from that distribution. The black line is what we actually found here. If the hypothesis, the null hypothesis, were true, how likely is it that we could be this far away from 100,000 on either side? That's the two-sided hypothesis test, p-value 0.07709. On the low side, that level or lower, the 96% p-value, this could be 100,000 or less is the one-sided p-value here of 3.8%, just this area. Go back to the two-sided p-value. It's close to this 0.05 magical incorrect number, but not quite enough evidence to say convincingly that it's not equal to 100,000. Notice what happens if I move the 100,000 that we're testing. If I wanted to test a hypothesis that the real mean was 101,519, we have an even less conclusive test. There's a 18% chance we could be that close to that mean. As I move this further and further away from what we found, the more convincing my evidence is. Could it be that the real mean is 98,000? Well, there's only a 2.1% chance we could be this far away on either side for a two-sided test from that mean of 98,000. So if the further away our evidence is from what we're testing, the more likely it is we're going to say we have enough evidence to basically say we don't really believe that hypothesis.
There's another animation, I'm just going to mention this once. It's usually a topic not even covered in most statistics courses, or at least beginning statistics courses, because can be extremely confusing, but it's actually a fairly important phenomenon. So I want to mention it. This is a power animation. We can also talk about the power of this test. And the power of the test has to do with the ability of the test that you're going to conduct to identify an effect or a difference of a certain size. So if you look at this diagram, what we have is the same red curve centered on 100,000. This is the hypothesized mean. If the hypothesized mean was 100,000, the red represents what we could get out of a random sample of 117 houses. What the blue shows is the same spread out distribution, the same t-distribution, which is essentially the same as a normal distribution, the same t-distribution, but centered on what we actually found in our sample, 106,274. The power of this test is the blue shaded area, and it's asking the following question. If the true mean, it's asking a question, how likely is it that the test that we're conducting would conclude that the real mean is not, would be unable to conclude that the real mean is not 100,000. Given that we found 106,000, the blue area represents the part of the red curve that is inside this region that we would not reject the 100,000 hypothesis. Remember, the red areas are where we reject, we're far enough away from 100,000 to reject it. The blue area represents, for what we actually found in this test, an estimated mean of 106,000, it's how likely it is that we would not be rejecting the 100,000 hypothesis. And it says there's a 42%, there's actually a 57% chance, that's what the blue shaded area is. We'd call the power of the test here 42%. It's the ability to detect a difference this large and declare it significant. Notice what happens here if I move this evidence further out. If we had actually gotten 111,564 in our sample, our power of our test to detect this larger difference now is 90%, because it's detecting it by saying that we would only fail to reject the 100,000 as the true hypothesis this fraction of the time given by the blue area. It's a much smaller area now because we're able to detect these large differences. If we were testing the hypothesis of 100,000 and we actually got 116,000 for the true mean, we have almost 100% power. 99.6% is the ability of our test to detect that larger difference. On the other hand, small differences, our test is not going to be able to protect against. If we actually had 103,376, if that was the true mean, the ability of our test to detect the difference between 103,376 and 100,000 is actually very small. Is only a 16% chance, a 1 in 6 chance that we would be able to detect this smaller difference. And a reason why we have not a very powerful test here is because the thing we're holding constant is this 5% cutoff for where we're saying we're far enough away from 100,000 to reject that hypothesis. By insisting on that standard of proof, we have opened ourselves to the inability to detect fairly small differences in mean. We can still pretty readily, 95% of the time, detect large differences in mean with that same test. So everything is geared to the red distribution and saying, how likely is it that we will
will be able to detect this big a difference, in other words, be in the red shaded area. And so it's sort of the reverse. The power is saying, how unlikely will we be to detect that larger difference? How often, if this were the true distribution, the blue, will we fall inside of the what's considered the acceptance area of the null hypothesis of 100,000, or failure to reject the 100,000. There's just no way around the fact that hypothesis testing has all of this language that's sort of reverse logic, double negatives, triple negatives. It just makes it really hard to talk about hypothesis tests. I prefer, think about the comparison now, to just focus on these numbers right here, because they give you all the same information, just much more readily. I'm 95% sure, somewhere between 99,300 and 113,000. Can I rule out 100,000? Well, not if I want to be 95% sure. Can I rule out 99,000? Apparently, 99,000 is below the lower end of this confidence interval, so I am able to detect that larger difference and remain 95% sure. Confidence interval is just a lot more direct, talking about what you get. Okay, well, that's a single sample hypothesis test. Let's ask another question. Let's say we're interested in the relationship between two things. How does the price depend on, let me change these data types here. Custom built, let's make that nominal. And let's make corner nominal. Custom built is an indicator variable, 0 or 1 for whether or not it is custom built home. 0 or 1 for whether or not it's on the corner. And actually, northeast is a 0, 1 variable for whether or not it's in the northeast part of Albuquerque. So let's take a look at a couple of these. Let's say, does price respond to whether or not it's custom built? My expectation would be custom built homes cost more, they're more expensive to construct. What you get in the display is two sets of points. One's for the custom built homes, one's for the non-custom built. Jump allocates the space on the x-axis to how common these are. Custom built homes are not as common as non-custom built homes, so non-custom built take up a larger space on the x-axis. Usually I turn that off in the display. I go to display options and uncheck x-axis proportional. Even though there is information in that display, I find it easier to look at the two with sort of equal spacing, because right now I'm not interested in the fact that custom built is less common than non-custom built. I'm really interested in the difference in prices. And what you can do is what's called a means ANOVA pool t-test. And there are several ways to interpret this. The easiest by far is the visual way. JUMP is providing you with a visual signal. These green diamonds represent confidence intervals for the mean in each group. And if the green, so we're saying that based on this evidence, the custom built group, the 95% confidence interval, and essentially I believe it's not the ends of the diamond, it's these little lines near the ends of the diamond. But essentially think of this green diamond as a confidence interval for the mean price of custom built homes. And this diamond on the left has the mean confidence interval for the mean price of non-custom built homes. If the diamonds don't overlap, essentially that's telling you there is a significant difference between these mean values. If the diamonds do overlap, it's telling you you don't have enough evidence to say there's significant difference. It doesn't mean that there is no difference. It's an absence of evidence, not beyond the burden of not beyond a reasonable doubt, we're not able to say there's a significant difference in means. The actual test that's conducted is down here. First of all, if you just look at the bottom table, you can see that there are 27 custom-built homes. The average value is 145,000 almost. And for the 90 non-custom-built homes, the average value was almost 95,000. That's quite a large difference in terms of dollars. Here's the difference in this t-test thing, 49,900, almost a $50,000 difference in values. Notice that the t-test says 1 minus 0, so it's group 1 minus group 0 is what it's reporting. If it was group 0 minus group 1, it would be a negative 49,000. So the way to interpret the 50,000 difference is group 1 has a $50,000 mean higher than group 0. Just like with testing for the value of the average price, there is a theoretical derivation of how likely, or taking two random samples, the difference in means, how big the difference in means can be in variability from taking one set of samples and then taking another set of samples and doing this many times. So the standard error of the difference has to do with the standard deviation associated with this difference between two means. And this t ratio over here is basically saying how many standard errors is the difference that we found away from 0, because the hypothesis we'd want to test here would be that there's no difference between the means. And we're saying, is there enough evidence to say there's a difference between the means? And so how many of these almost $7,000 standard errors is our difference of 50,000? It's 7.16 standard deviations away from 0. If we test the hypothesis that there's no difference between the means, when we take our random samples, we should be somewhere under this blue curve. And here's what we found, this red line out here, which is actually 7 standard deviations above the mean. The chance of being that far above the mean is essentially 0. That's why it's telling you the p-value is too small to measure. What JUMP says about small enough to indicate very convincing significance. P-values are the probability we could be this far away or more, given that the true value of what we're trying to measure here, the difference between the means, is at the hypothesized level of 0. More directly, look at the confidence interval, which is basically telling you, plus looking at the difference that we found, plus or minus approximately 2 standard errors. The confidence interval is somewhere between 36,000 and 64,000. So I'm 95% confident that the difference between custom-built homes and non-custom-built homes, the average price, is somewhere between 36 and 64,000. It's nowhere near 0. It's a positive difference. I'm pretty confident that custom-built homes sell for more. Hypothesis test gives you the same result as the confidence interval. The confidence interval is just a more direct way of doing that. You will notice that I skipped over, there is another thing that's being said here. It says assuming equal variances. One way to do this test is, this is what's called a pooled t-test. And you will notice when I click the red arrow, it said pooled t-test. There's an assumption being made that these two random samples have the same standard deviation, the same variability. And the importance of that is if they have the same variability, then they pool them together to estimate what the population variability is of all houses together. If you don't make that assumption, then each of these groups, non-custom built and custom built, are treated separately. And they're used the standard deviation in each group alone to estimate what the standard deviation is in that group and in that group separately. And the formula is more complex, and the result is that the test is a little more uncertain, because instead of using both pieces of information, all 117 houses, to estimate a single standard deviation for the price of houses, we now have to do 2 separate estimations. What is the standard deviation of custom-built homes? What is the standard deviation of non-custom-built homes? Use each of those sample standard deviations to estimate each of those separate standard deviations, and it results in more variability in the test that we're conducting. What does that look like? You can actually do that test. You can ask for t-test. The t-test basically does not assume that it does not pool together the 2 samples. It treats them as separate. And when you do the t-test down here, it says assuming unequal variances. And instead of being 7.16 standard deviations away from zero, we're only 5.2 standard deviations away from zero. The p-value is just as small as before. Notice the confidence interval is a bit wider. Instead of being 95% sure, it's between 36 and 64,000. It's between 30,500 essentially and 69,400 or so. So it's a wider interval representing the increased uncertainty by not making that pooling assumption. And if you really want to get detailed about this, you can say, well, what can we say about assuming that the standard deviations are the same in the two groups? That pooling assumption, is it a good assumption or not? You can click unequal variances, and JUMP does 5 different versions of a hypothesis test that the variability in each group is the same. So it's tests that the variances are equal in the two groups. I frankly have never looked at what the details of these 5 different tests are. There's 5 different versions of the tests that statisticians have come up with for testing this kind of hypothesis. They don't always tell you the same thing, but in this case, all 5 of the tests give you p-values that are sufficiently low to reject the hypothesis that the variability is the same. They're clearly not the same. One group is more variable than the other. We should not be doing the pool t-test that was done at first. We should be doing a non-pool t-test, which is the second test. And it gives you another version of that test as a result, testing the means equal, but allowing the standard deviation to not be equal. I can tell you from looking at hundreds of examples, maybe thousands, I believe I have seen only one case, and I can't remember where I saw it, where the unpooled t-test and the pooled t-test gave you qualitatively different results. They'll always give you a slightly quantitatively different answer. So I don't think you have to worry about this. I mean, there's a lot of money at stake. I mean, it's a one mouse click to get both tests. You might as well look at both and see if they're qualitatively different, but I don't expect them to be. This is one of those subtleties that's really not of any consequence. Let's do another one of these. Suppose we look at whether the price varies with whether or not houses are on corners. And I think you can see visually the first one, the non-corner houses seem to be more variable than the corner houses. So we shouldn't be doing a pool t-test. We should probably do the t-test. I'll go ahead and just do that. P-value is 0.27. It's a 27% chance if we test the hypothesis that the two means are equal. There's a 27% chance we could come out as much as $7,687 difference between the two means. The confidence interval ranges from a minus 21,492 difference, meaning that group 0 had a higher mean than group 1, to a plus $6,117 difference. Group 1 has a higher mean than group 0. So if we're 95% sure, it's anywhere from group 0 being higher to group 1 being higher. It's another way of saying we really can't say with any confidence, at least 95% confidence, that the two means are different. So does having a house on the corner increase or decrease the value? We're unable to say we have enough evidence to pick that signal out from amidst the background noise. And the reason is not so much that the means are close together. 7,700 is a fair amount of the difference between the two means. It's more the background variation is so large that we're unable to confidently conclude that the means are different. The reason I generally do the pool t-test is usually it doesn't give you a different result and you get a nice visual explanation where you can look at these diamonds and clearly they overlap here. So even if you don't want to get bogged down in the numbers and interpreting either the hypothesis test or the specific confidence interval, your eye quickly sees that these overlap to such a great extent that we really can't say there's a signal amidst that background noise. We're not saying that being on a corner has the same value as not being on a corner. We're just not finding enough evidence to say that it's different. So that's what's considered a two-sample t-test. A second test we could do here is to be looking at how does the price vary with square feet. Notice we use fit y by x. Jump, let me go back and do that again. When you do fit y by x, Jump actually does 4 different potential analyses depending on what kind of variables you have. When they're both continuous, it's looking at this top left, it's doing a bivariate plot. The last one we did, we had a continuous y variable, but our x variable is nominal. We're doing a one-way analysis of variance, which is where we got the t-test. If both variables are nominal, we'll look at an example of that in a minute, we get a contingency table. And if the y variable is nominal and the x variable is continuous, we get a logistic regression. And I'm not going to talk about that in this lecture, but we will look at that in some detail. It's just as easy to do the test, but interpreting it is a little trickier. So we have 2 continuous variables here. The display we get is a pretty common one to look at, a scatter plot. What we're trying to do is say, what kind of relationship is there? And can we be confident about that relationship? Well, one thing to possibly do is say, well, what would a linear relationship, if we want to say on average, there's a straight line relationship between these two, what would that look like? I think you could, let me draw one in visually. Seems to me if I were drawing a straight line to represent this, I would probably draw one something like that. If we actually want to draw the line that fits best, where the definition of the regression line is it minimizes the differences of the points from the line. It actually minimizes the sum of the squared distances. So it penalizes for getting a line too far away from any point. So literally, it's looking at all possible straight lines it can draw, measuring the distances of all the points from that line, squaring those distances, and finding the line that has the minimum sum of the squared distances of the points from the line. When you do fit line, Jump solves that problem, and the red line is the true least squares regression line, pretty close to what I was drawing. When you look at the red line, it gives you first the equation for it. It says price is equal to $4,782 plus $61.37 per square foot. The intercept, usually you don't want to interpret, doesn't make any sense to interpret. Here you could put it in words. What does the intercept represent? It's what the price of a home would be when it has 0 squared feet. Well, what's that? That's an empty lot. The reason why even though you could interpret it as an empty lot, I would be very unwilling to say that's our estimated value for an empty lot. Our data set's all houses. We have no data on empty lots. Without any data on empty lots, I'd be reluctant to say we have any evidence about what the value of an empty lot is. I prefer to think of the intercept as just the mathematical fact that a straight line has to go through the y-axis somewhere. This happens to be where it goes through. None of these points are at 0 square feet. The model that we built here, a very simple model, really is this one number here, the 6137, because it says as you change square feet, each additional square foot is adding that much to the value, 6137, which is not a bad measure in mid-1990s of construction costs in Albuquerque, so it's a pretty reasonable number to come up with. We get some other measures here, r squared. I will at some point talk about why r squared is not a very useful thing to look at, but it's the thing that students remember the most, and it's sort of probably a single easiest measure to look at as to whether or not this is a good fit. When I look at this picture, does the red line reasonably describe these points? Seems to me it's not a bad model of these points. The points are clustered sort of near the line, not perfectly on the line. 0.71 for the r squared is the value between 0 and 1 indicates what fraction of the variation in the prices is accounted for by the x variable, the square footage. 71% of that variation is accounted for by the size of the house. You're tempted to say the size of the house is causing 71% of the variation in prices. And in this case, I think causation is a reasonable thing to be thinking about, but correlation is not causation. So this is simply a measure of how close the points are to the line. If these points came out exactly on the line, we'd have an R squared of 1. If the points were completely randomly scattered all directions from the line, we would be getting an R squared of 0. 0.71 is reasonably high. Let me take this line out of the picture so it doesn't cloud us up. We also see that there are parameter estimates here. This is the equation for the line again. Here's the intercept, and here's the square foot coefficient. The square foot coefficient is the one we're interested in. And we could actually test a hypothesis, or we could look at a confidence interval. Let's start with the confidence interval. If you right-click and go to columns, take the lower 95% and the upper 95%. How much does a square foot add to the value of a home? Well, our point estimate from these 117 houses is 6137. But if you want to be 95% confident, you'd have to say it adds anywhere from $54.19 to $68.55. That's the meaning of that confidence interval. And again, of course, technically, the confidence interval is just that if you did repeated random samples, 95% of the time, whatever these two numbers are, would contain the true coefficient that relates square footage to price. But that's of no use here. We have one sample, so I'm going to use the incorrect technically interpretation that the true effect of square footage on price is 95% sure it's in this range. Or we could construct a hypothesis test. We could test a hypothesis that there's actually no effect of square footage on price, which Andrew Gelman would say, that's never going to be true, and it's never interesting, and it's not interesting. I mean, we know the size of the house affects its price. But if you wanted to test a hypothesis that there was no effect, these variables are not related, the real coefficient would be 0. The question is, are we sufficiently far away from 0 on the slope of this red line to reject the hypothesis that there's no relationship? Well, again, there's a standard error associated with this estimate. That standard error has a fairly complex formula here about how much random samples you would expect to see the estimated coefficient vary from one random sample to the next. And the t-ratio is measuring how many of these standard errors our estimated coefficient is away from 0. It's actually almost 17 standard deviations away from 0. How likely are you to be 17 standard deviations away from 0? Well, the answer is almost impossible to happen. So when you look at a bell-shaped curve, it's basically a standard normal distribution, you're 99.6% of the time within 3 standard deviations. Being 17 standard deviations away is not going to happen. This is very strong evidence to reject the hypothesis that the real coefficient is 0. And I could actually show you what that would look like if I do fit mean. This green line is the hypothesis we just tested. If on average there's no relationship between square footage and price, the green represents the average price of homes in this sample. And so what we're really testing is, could the green line be the true relationship? And these scattering of points just happens to be due to random sampling. We just took a random sample of 117 houses and they turned out to look like this. Well, it doesn't look like very randomness. If we look at the odds that you're going to get a random sample where at the low square footage all the houses tend to be below the line, and at the high square footage they're all above the line. And in fact, the best fitting line has a slope of 61.37, the red line. The chance that the red line is what we get from a random sample where the green line is the true relationship is just not going to happen. So in fact, we can reject the hypothesis that the green line is a true relationship. There is in fact a positive relationship between square footage and price, which of course the confidence interval has already told us. So as usual, confidence interval directly tells you what you want to know about the relationship between these variables. I'll just mention right now that it doesn't have to be a linear relationship. If there's a relationship, it could take some other forms, and JUMP gives you quite a few possibilities. You can fit sort of quadratic relationships, which would be the blue line, and that makes some intuitive sense to me. Big houses are worth more, but there's some limit to this because really big houses aren't as appealing. They're expensive to heat or cool in the case of Albuquerque, actually both. And there's just less appeal. They're harder to clean unless you have a really huge family. The idea of having a really big house is not as appealing as sort of diminishing marginal returns to the size of a house. And that's what the blue would show you here. And we could examine the equation for the blue. If you look at the equation for the blue, this quadratic equation, the square term, notice, also has a very low p-value, telling you that you can reject the hypothesis that the square term really is zero, which is what a linear relationship is. It's saying only the linear term matters. There's no square of square footage that matters, but it's saying that you still have some signal in the square of the term. It's probably a better fitting relationship. Notice the r squared is 0.73. It's a little bit higher than it was for the linear relationship. And you can try fitting lots of things here. I would recommend never fitting 6-degree polynomial unless you have some reason to be able to interpret that. But you can also fit logarithmic relationships, square relationships, all sorts of things built in. This is actually why I originally adopted JUMP rather than the software I had previously been using. It's the ease of graphically just seeing what these different relationships look like. Okay, let's look at another kind of relationship. Suppose we want to know whether custom-built homes are related to whether or not a house is on a corner. Is it more likely that people build houses on corners that are custom built or are not custom built? Two nominal variables, we're going to get a contingency table. Contingency table by default gives you a bunch of numbers in the table. It gives you the count, how many houses are in each of the 4 cells. It gives you the percent of the total 117 houses that are in each of the cells. I can tell you that total percent is never what you want, so I would get it out of the picture, uncheck it. And if you set this up right, it's almost always the row percents you want. So you want to know of the custom-built homes, what percent are on the corner, what percent are not. Or you could look at it from the point of view of the corner homes, what percent are custom built and what percent are not. Usually if you ask the question the right way, does Y respond to X? Does being on a corner respond to whether or not it's custom built? Then you would want the row percents, and actually I'm going to do this over because I think the easier way to think about this intuitively is to ask, does custom built respond to whether or not a house is on a corner? My hypothesis would be that you're more likely to build a custom built home if it's not on a corner, since corners are kind of crowded, involve traffic, you may not want to be there. So I will take out the total percents and the column percents. What do we have in our sample? Of the houses not on a corner, 23%, 23.16% are custom built. Of the houses on the corner, 22.73% are custom built. So if they are in a corner, a slightly lower percent are custom built. The statistical inference question is not to look at these two numbers and say, is that a big difference? Because it has to be compared to something. And the question is, in a sample of 117 houses, is that a large enough difference that we are detecting a signal out of the noise. And intuitively, I don't think you really can answer that question. I don't think our minds are set up to be able to factor in the sample size and how much variability there would be. So you really have to do a test to find out how large those differences are. And that test is shown below here. There are actually two versions of what's known as a chi-squared test. They're slightly different, although they give exactly the same number here. And basically, it's telling you, if you look at the p-value here, well, there's either these two p-values here or a p-value, there's a third version that's given here. The p-values are enormously high. It's basically saying these numbers are too close together to be able to say there's enough evidence that there is a difference in the fraction of houses that are custom built on corners versus not on corners. In other words, we can't safely say there's a relationship between whether or not a house is custom built and whether or not it's on a corner. Unfortunately, from this display, you don't get a confidence interval. If you wanted to get a confidence interval, then you would have to do this somewhat differently. You could ask for the distribution of custom built by corner. This is, I'm cheating a little bit on this, but it'll give you the basic idea. So we got the same numbers again here, the 23.158% among the not corner houses, and in the corner houses, the 22.73%. So the same numbers appear here. But from this platform, we could actually test probabilities. So we could say, is it possible that for these non-corner houses that the percents would look just like they do for the corner houses? So we could put in the numbers from the second table. So I'm just taking the probabilities from the corner houses and saying, for this sample of non-corner houses, could those be the true fractions of houses that are custom built and non-custom built? And p-value pretty high, 0.92, not exactly the same numbers you get here. This is technically not exactly the right test to do, but it's the right idea. It's basically saying, well, the reason I did this was to try to get a confidence interval, which I didn't give you, so I should have instead asked for the 95% confidence interval. So there it is. We look at the non-corner houses, and I guess we could do the same thing here. This is what I meant to do instead of testing these. Compare these confidence intervals. The custom-built non-corner houses, it's from 15.8 to 32.6%. For the corner houses, it's from 10% to 43%. It's a much wider interval because we have fewer custom-built homes. More variability can be expected, but 10 to 43 certainly contains the 15 or 16 to 33%. So that's why we're unable to say that there's enough evidence of a difference here. I can actually show you the way this chi-squared test is actually done. You can actually build that into this table just because it's kind of neat to see. But there are a series of steps here that underlie the chi-squared test. First, it's calculate an expected number. So we found 73 houses, non-custom built, non-corner. If, in fact, the hypothesis was true that there's no relationship between these two, what these numbers that are now shown at the bottom, these strange numbers with fractions, they're actually derived by saying, well, what fraction of the 117 houses were custom built? what fraction is 27 of 117? It applies that same fraction to the 95 houses on the corner and the 22 houses not on the corner. And that comes up with these expected numbers, 21.9231 and 5.07692. And conversely, what fraction is 90 of 117? Applies that fraction to the 95 and the 22 houses to get these left-hand bottom numbers. The next step in the chi-squared test is say how far away is what we'd expect under that null hypothesis from what we actually found. So this is just measuring those differences. Then it gets a cell chi-squared, which basically says how far, look at the deviation from what we would expect if the hypothesis were true that there's no relationship between these two variables. What is that deviation divided by the expected number squared? So you look at the deviation divided by the expected number, so we're looking at minus 0.0769 divided by 73.07 and squaring it. And then the chi-squared test actually adds up these bottom four numbers. And it's, I forget which of these two tests, they'll usually give you slightly different numbers. I'm not sure if it's the Pearson or the likelihood ratio test, but if you add up those four bottom numbers, it should add up to one of these two. In this case, they're both the same. So that's how the chi-squared test is done. It's sort of logical. It's saying, if the null hypothesis is true, there's no relationship, we'd expect to find the same fraction of both corner and non-corner houses would be custom built. What would that fraction be? How far away is that from what we actually found? Scale it by dividing by the expected number and square it as a measure of how far away we are from what we would expect under the null hypothesis. And that's the hypothesis test. If you look at a chi-squared distribution, unlike the normal distribution, the chi-squared distribution is a skewed distribution and it's only positive numbers. And I think you actually get the chi-squared distribution by squaring the normal distribution, something like that. There's all kinds of funny mathematics going on in the background, but the whole idea is that if you have things that are normally distributed, but you square them, you only get positive numbers, and the question is how large is the positive numbers that you're getting here? Are they far enough away from zero difference to basically say there's a significant relationship between these two? Because we're looking at the differences between the fraction that we found, the percent of the houses, corner and non-corner, that are custom built from what we would expect to find if the hypothesis was true that it's unrelated to whether or not the house is on the corner. So we're looking at how much is related, the percents that are on the corner and are on the corner and not on the corner, to what those percents would look like if we in fact had no relationship and the same percent of houses on the corner and non-corner were custom built or not custom built. So that's yet another hypothesis test. Let me go over one other type, and I think I will postpone to another lecture going over some yet another kind of test. We have number of features here. The number of features is a continuous variable because it's measuring number of features. The features, if you read about it in this data set, are actually, I may have put notes in, let me see if I did. Yeah, number of features out of a list of 11. And the 11 features were things like dishwasher, garage, garbage disposal. It's a bad measure. Measurement is important, and in this particular case, this is a really bad measure. I really want to not lump these things together. A garage is a big deal, whereas a dishwasher is not as big a deal. In fact, if it's a fairly old home, having a dishwasher usually means you probably have to replace it. It's not going to be working very well. The garbage disposal, almost always, every house I've had, the garbage disposal needs to be replaced. So I would consider that almost a negative feature, whereas a garage is really quite valuable and an important feature. This just added up how many are there out of the 11. And it is measured as an integer value, but it's not really continuous, but it could, 7 is more than 6, but especially since these features are not sort of equal, I think it might be more appropriate to treat it as a nominal variable. And we could say, does the price of a house respond to how many features there are? Y variable is continuous, X variable is nominal. This is one-way analysis of variance, just like we did with the t-test. The difference is that instead of just 2 groups, we have several groups because the number of features seems to range from 0 to 8. The space on the x-axis is proportional to how common these number of features are. We see there's only one or two, I think one house that has 8 features, and there's 2 houses that have 0 features. I think it's easier to look at the display if we uncheck x-axis proportional, so they all get equal spaces. When you want to do an analysis of variance here, which is the proper test to do in this case, it's the second option, mean, ANOVA. Notice it doesn't say pool t-test anymore because that t-test is for when there's 2 groups, and now we have 8 different groups. And what it's going to do is give you green diamonds for confidence intervals for the mean in each group. Notice the huge confidence interval at 7 and 8 because we only have a single house there, and it's a pretty large confidence interval at 0 because we only have 2 houses there. As we have more and more houses with these numbers of features, we have somewhat narrower diamonds. We can be a little more sure about what the average value looks like. And what an analysis of variance test does is it basically tests the hypothesis that every group has the same mean. In other words, there's no relationship between price and number of features. No matter how many features there are, every group, every number of features has exactly the same mean. You have to consider analysis of variance as a 2-step process. The first step is testing the hypothesis that all of the groups have the same mean. And if you have a lot of groups, it almost always is going to reject that hypothesis. It's not particularly interesting to say, is there no difference between these groups? What you really want to know is which number of features are more valuable, not are they all the same. Well, if you do test that they're all the same, here are the mean values in this table, and you're almost always going to reject the hypothesis. And in fact, you can here basically look at these green diamonds and you're saying, is there any set of green diamonds that don't overlap? As long as one of the green diamonds lies above one of the others, they're not all the same. Here's the result of the hypothesis test that they're all the same, and its p-value is very low. It's less than 1/10 of 1%. So if, in fact, it were true that all houses, all different numbers of features had the same average price, we are far enough away from that to safely say we can reject that hypothesis. The way the hypothesis is actually done is it basically does 2 kinds of calculations. It says, it looks at this, this black line, which is known as the grand mean. That's the overall average price of houses, about 106,000 here. And then it looks at the mean in each of these separate groups. And it basically says how far away is each of the group means from the grand mean. And far away is measured by taking the squared sum of those distances. So that's in this table shown as the sum of squares, and it's for the number of features. There are 8 different groups. It's taking, there's actually 9 different groups. Degrees of freedom is this funny statistical term. In this case, it's the number of groups minus 1. So there's 8 degrees of freedom. There are the sum of these squared differences of the means from the grand mean is the sum of squares. And the mean square is the sum of squares divided by the degrees of freedom. The error sum of squares has to do with looking within each group and saying how far are each of the individual points from the mean for that group. So we're looking at the first measure was between group variation. Just look at the group means and say how far away are they from the overall average. The within group variation says look at each group alone and say how variable are the individual points from the mean in that group. It will always come up to a much bigger number. Instead of 10 to the 10th power, it's 10 to the 11th power here, because there's a lot more houses individually than there are groups. So you're going to get a lot of variability, especially when you square the differences of each of these points from the mean in that group. So to sort of put them on a similar scaling, it divides the sum of squared these error terms, which the reason they're called errors, they're unexplained here. We can explain the difference between the mean of group 2 and group 6 because it's associated with how many features there are. Why the individual houses with 2 features vary, we have no idea because there's no data on that here. We've just basically saying that's random variation. So it's called the error sum of squares. And you divide it by the total degrees of freedom, which is the total number of observations minus the degrees of freedom associated with the features minus 1. So this is more akin to the total sample size that we're looking at for the error degrees of freedom. The mean square is looking at the sum of squares divided by those degrees of freedom. And then there's finally an F ratio, and F distribution sort of looks like a chi-squared distribution. It's only positive values and it's a skewed distribution. And the F ratio is taking this mean squared divided by this mean squared. And then there is a complicated table that the computer has built in to look at an F distribution to basically say, with these different numbers of degrees of freedom, is this far enough away from 0 to say it's significant? And the reason why 0 would be a useful number is think about the way it's constructed. If the difference between the group means and the grand mean is very large, so think about these diamonds as being very spaced apart. There's a lot of difference between the group means and the overall mean. But the points within each group are very narrowly spaced, so not like it looks here, all these points are sort of within a very narrow range. We'd have a very large number, mean square for the features, and we'd have a very small mean squared for the error. This ratio would be a very large number. The larger this number is, the more likely it is that there's some significant variation between the groups. On the other hand, if these group means are pretty close together, so there's not a lot of difference between the groups, but within the groups, the difference is very large, then we have the mean squared for the features being a small number compared to the mean squared for the errors, and this F ratio would be a very small number. And the smaller it is, the less likely it is that we have found a significant difference between these different groups. So the way you think about the analysis variance test is it's measuring the within group variation or the between group variation compared to the within group variation. The larger the between groups variation is compared to the within group variation, the more likely it is you have found something significant. Now, as I said, that's only the first step. Once you find that there is some significant difference, and this is telling you that these are not all the same, these groups, you want to know which groups are different. So when you go under the red arrow to compare means, there's 2 basic methods to look at here, and they're 2 extremes. You could compare each pair using a student t-test. And what JUMP is doing is it's basically creating a bunch of subsets of data. It's saying, let's just compare group 0 and group 1. No features and 1 feature. Throw away the rest of the data, pretend it doesn't exist. And just do a t-test on whether there's a difference between 0 and 1. And it does this for all the possible pairs, and it gives you more ways of looking at this that you possibly could want to know. One way is called the LSD, which is not a drug here. It's called least significant difference threshold matrix. Any positive values are means that are significantly different. Negative values means you don't have enough evidence to say that they're significantly different. So you can isolate which ones are significantly different. By far, not the easiest way to look at this. The connecting letters report takes a little getting used to, but it's actually a pretty easy way to describe it. Any levels levels being number of features, not connected by the same letter, are significantly different. So when you look at group 7 and group 1, they're significantly different because they don't share a letter. Group 7 and group 6 do share a letter. They're not significantly different. Let's look back at the picture. 7 and 1, the diamonds don't overlap. 7 and 6, they do overlap. So connecting letters works. Here are all the pairwise comparisons shown, along with how big the difference is, the standard error associated with it, a 95% confidence interval for the difference, and it designates a p-value for each of these separate t-tests and color codes. The orange are less than 0.01. The red are between 0.01 and 0.05, and the black are above 0.05. So it's a measure of, in a sense, how strong the signal is compared to the noise, and then there's a graph that goes along with that. And if that wasn't enough, it gives you one other way to look at that. And this one's a riot. I mean, you should read the help feature and jump on this. The circles sort of could make sense if you were looking for circles that, do the circles overlap or not? But that's not the way you read these. Each pair of circles, what you have to do is, when you compare two circles, you have to draw lines tangent to the two circles and ask whether the angle between them is less than 45 degrees or greater than 45 degrees. And that tells you whether or not that's a significant difference. So you could look at it that way if you want. I have never done that and will never do that. Or you could look at it using the least squares, the least significant difference threshold matrix. Give you the same answer, just a different way. I wouldn't do that either. Connecting letters report, which is reasonably compact way to describe this, or the order differences report, which is rather lengthy but very easy to interpret. So that's one extreme, and the reason why this is really not the recommended way to do it is basically to throw away all the other data and just pretend that you only had each of the two groups each time you do it. You're committing a logical mistake because you're doing a whole bunch of comparisons here, each one of which is pretending that none of the other comparisons are being done. And if you really want, if you're using 5% as your threshold for saying that's enough evidence that the signal is large compared to the noise in the background, you are cumulatively running more than a 5% chance of making a mistake in one of these comparisons, because each comparison is being done in isolation when in fact we're doing a whole bunch of these tests. One way to look at it is look how many different t-tests we just did here. Each one might be subject to a 5% error, but if you do enough of these tests, almost guaranteed that one of them is going to be wrong. So there is another way to do this. Compare means, all pairs, Tukey is a famous statistician. The HSD stands for honestly significant difference. Tukey said, let's take into account that all of these tests are going to be done at the same time, and let's limit the chance of making a mistake, wrongly declaring that we found a significant difference when there is none. Let's limit that to 5% in total across all the tests we're going to do. You get a different set of these circles, equally unintelligible. You get a different, honestly significant, different threshold matrix. Positive values are significant differences. Negative ones are not strong enough to say it's significantly different. A different connecting letter report and a different comparison difference. You can see what the difference is. This very conservative test now, very few differences can you declare to be significant. Group 7 is higher than group 0, 1, or 2. And those are the only things that you can say are different. And those are the three comparisons that show p-values that are less than 0.05. So personally, what I think is the Tukey test is a more legitimate test, but when you have a lot of groups, it seems to me a little overly conservative, because if you have a lot of groups, you're doing a lot of pairwise comparisons, really puts a pretty high burden of proof on finding something that is really significantly different amidst all of those tests that you're doing. The simple comparison using each pair student t-test is clearly not conservative enough, because if you do enough tests, I guarantee you're going to be making type 1 errors by wrongly declaring that there's a significant difference sometime amidst all those tests you're doing, and pretending each test is in isolation where none of the other tests are being done is not conservative enough. So in truth, it's probably somewhere in between. And if it really matters, you know, there's money at stake in the answer to this question, then I think you should probably do both and compare the results and have to come to some decision of how conservative you really need to be for the particular difference that you're interested in. So that's analysis of variance. Certainly a lot going on in that. But the thing I would say where I'll end this particular video is all of these tests have, they all have mechanics behind them, but they're all asking the same basic question. They're saying, let's look at something and say, is there some relationship here? Is the noise large enough? Is the signal large enough compared to the background variation to say we have found something of interest that we're pretty confident on? And they all share a fault that they're taking relatively something like two-dimensional slices from a multi-dimensional picture. Here we're isolating just number of features versus price. We looked at corner versus price. We looked at custom built versus price. We looked at square footage versus price. What we really need to do is take into account all of these factors at the same time, because it is a multi-dimensional picture that is affecting the price, not each of these single slices. So that's where the next lecture will come from, looking at multiple regression analysis. We really need to account for multiple variations, multiple factors at the same time, because it can be extremely misleading to look at these single dimensional pictures. And if you think about any real study that's reported where they say, well, we tested 2 groups and one group adopted power poses before they gave talks and the other group did not, and then we had ratings on the speakers at the end and we found a significant difference. The question is, how many other variables were also different at the same time? Usually you can't control the experiment to the point that there's only one source of variation and you observe one outcome. In natural sciences, of course, it is easier to do those kind of experiments, but in anything involving people, you usually have multiple things changing at the same time, and it can be extremely misleading to isolate one dimension and try to do a test on it. So in the next lecture, I will cover multiple regression, which brings together a lot more influences at the same time.